Hello, Year 13 doubles. We're coming up to the real juicy bits of the chapter, which are, no doubt about it, really quite challenging. But that's good. That's good. This is a fun chapter to teach purely because it's probably one of the most difficult things you'll do in further maths. It's brilliant though. It really is great fun. Now, I want to start by saying I'm basically going to talk you through what you need to know before doing exercise 1E. But one of the things I certainly want to say is you've got to develop flexibility in terms of going from one format to the other. So, for example, if I wrote down for you e to the I pi over 2, I hope that you can immediately see that that equals I. I mean, okay, not immediately, but I hope you can gradually get to the point that you see that that equals I. Now, you might think, how do I know that equals I? Well, there's lots of ways of seeing that that equals I. Probably the easiest way is to go straight into the cos plus I sine format. Sorry, I'm writing sine first, apologies. So that's the same as cos of pi over 2 plus I sine of pi over 2. Well, you can see it immediately now because cos of pi over 2 is 0 and sine of pi over 2 is 1, and so it equals I. But the other reason that you should be able to see it straight away is because this complex number is written in the form re to the I theta. Now, what do r and theta represent there? R represents the distance you are from the origin, and so clearly you're a distance of 1 because it's just e to the I pi over 2. And theta represents how far you need to turn from the positive x-axis. So, the positive x-axis is obviously here, along that bit. We need to turn pi over 2, which is 90 degrees, and we're 1 away from the origin. That means we're definitely going to be I up along the imaginary axis, if you see what I mean, because pi over 2 is a right angle. Do you see what I'm saying? It's about how far you turn. So I wondered, would you like to just pause the video perhaps while you quickly work out what e to the 3i, well, I times 3 pi over 2. I'm going to write it as 3i pi over 2 because it would normally be written as that. If you had that, what's that going to be, I wonder? Pause the video right now and quickly decide. Hopefully you can see that that's going to be minus I because you've turned through a pi over 2, another pi over 2. So that's pi over 2, that's another pi over 2, and then another pi over 2 as well. So you're now at minus I. And I hope you can see that e to the 2 pi I, it'll probably be written like that. It depends, the order's kind of like, sometimes it's written one way, sometimes it's written the other. But if you've got e to the 2 pi I, well, that's just the same as e to the 0. It's 1. You've turned the whole 2 pi radians around the axis, and so it's 1. Don't be afraid of arguments that aren't stuck between minus pi and pi. We use that all the time in complex numbers. It's just by convention that we write the argument between minus pi and pi, but we can certainly go beyond that on either side. So do be flexible with the way you write complex numbers. It will really help you in lots and lots of these questions. So that's the first thing I'd say. Okay, let me write down some more things which I think are crucial to know though. I'm just going to do some rubbing out very quickly. That formula, that e to the, well, I'd like to clear the board, but I want to keep the title up there. And I've got some rubbish little scribbles down here. But I want to write down things that you have to know before attempting these questions. So certainly the fact that e to the I theta is cos theta plus I sine theta, that is hugely important. Yeah, like Euler's relation. Notice that there's no theta or i's in the sine or cos there. That is just a standard result. You've also got de Moivre's extension on that, which is that e to the I n theta is cos n theta plus I sine n theta. You might be thinking, oh, where's the old r? Where's the modulus gone? We don't tend to use that so much in the next bit of the chapter, but so that's why I'm not mentioning it for the next exercise, but it's definitely still true. The full de Moivre's theorem, which includes the modulus as well. And then I want to talk about two things which popped up in the last exercise. Okay, because we know that this is true, e to the I n theta equals cos n theta plus I sine n theta. If we let z equal this, we could also, or z to the n equal that, yeah? In other words, z is just going to be e to the I theta, but that's also cos theta plus I sine theta. Yeah. Well, then z to the n is going to be e to the I n theta, which is cos n theta plus I sine n theta. I'm just going to derive a couple of results which we already knew. Note that z to the minus n, which is e to the minus I n theta, which equals now. Let's do this very quickly. All right, I will write down one line for you. That's cos to the minus n theta plus I sine to the minus n theta. But that can be immediately rewritten as cos n theta minus I sine n theta. And from that come the two results which we're using in the last exercise all the time. And that is that z to the n plus 1 over z to the n plus z to the minus n. Oh, well, that equals 2 cos n theta. Yeah, you need to memorize that. You really do. And in particular, bearing in mind that z to the n is e to the I n theta, what we could say is that e to the I n theta plus e to the minus I n theta is 2 cos n theta. And likewise, because z to the n minus z to the minus n is 2i, and you can just quickly work that out by subtracting the 2, you're going to get 2i sine n theta. We can conclude that e to the I n theta minus e to the minus I n theta equals 2i sine n theta. Yeah? They're really important results. In many ways, you can ignore the n and just think of it as e to the I theta plus e to the minus I theta is 2 cos theta. Yeah, by all means, do that. But quite often, we're going to be using it with powers as well. So these results are really crucial. In fact, I might just write down the simpler version because I feel like with the n, we're sort of overdoing it because n theta is just like u. You'll more often see it as just e to the I theta plus e to the minus I theta is 2 cos theta, and e to the I theta minus e to the minus I theta is 2i sine theta. Yeah, we're going to be using all of these ideas in the next chapter, and we're going to use them. I mean, the next exercise, sorry, I keep saying next chapter, the next exercise is only 7 questions long, but it will take you a couple of hours. It's all I'm setting you for the rest of the week, but I do want you to do every question. And what's more, I'm quite happy to upload my solutions to every question on YouTube, but I want you to have a go at it first. I really do. You've got to try and get as far through these questions as possible, but it is, you know, it's a nice challenge. They're great fun. They really are. Let me take you through the first example. Yeah, it just says, okay, right, and I'm not going to introduce the sum of series formula because I've just given you enough to remember, and I think you already know, I'm sure you already know, surely you already know that the sum of n terms for a geometric series is, well, let's write it down the other way because we normally do it the other way, r to the n minus 1 over r minus 1, and the sum to infinity is a over 1 r minus 1, 1 minus r. Let me just take that back. If provided that r is between 1 and minus 1. Yeah, those formulas we're going to use. That's what this whole next exercise is about. It's about sums of series. Yeah, I don't think you need to memorize their ones with sigmas, w's, and z's. I think really they're just simplifications of these, and I've never memorized them, and you don't need to memorize it. So, okay, without further ado, I'm going to go through example 13 because I suspect that if you read example 13, you'll probably scratch your head and think a little bit like, ooh, that's that's quite nasty. I'm going to show you how I would have done it first, but then I'm going to show you how they did it, and I'm going to talk about both approaches and say why you need to understand really both approaches because both are useful. Okay, so example 13, it says given that 1 plus z squared all the way up to and including z to the n minus 1 equals, oh sorry, no, it doesn't say that, we've got to prove that. Sorry, so given that z equals cos theta plus I sine theta, So they've not really given us much there. They've just given us a standard definition of a. Oh no, 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 no. Oh, blimey. Let me just start again. I'm not actually looking at the textbook, which I need to be because there's quite a few details here. Okay, so start again. Given that z equals, right, cos of pi over m plus I sine of pi over m, prove that 1 plus z squared all the way up to z to the minus n minus 1. Prove that that equals 1 plus I cot pi over 2m. Yeah? Now, when I looked at this question a couple of nights back, because I thought I'll work through the complex numbers chapter because I know it's got some really tricky exercises in it. Well, when I looked at this example, I thought, okay, I'm going to prove it myself first. And I actually did it in a different way to them. And I want to show you the way I did it. And I want to talk through my reasoning about why I did that. Now, basically, I did it because I wasn't thinking about some of these formulas up here, but I was just thinking in my head, what can I do? What can I do? Now, I started with the left-hand side, and the first thing you should notice is this is a geometric series. It's a geometric series with first term 1 and common ratio z, yeah? Because we're multiplying by z each time to get to the next term, and it's a sum of a series. So what we've got here is a times r to the n minus 1 over r minus 1. Now, our a is 1. R is z, so it's going to be z to the n minus 1 over z minus 1. And that's just because it's geometric. It's a geometric series. Yeah? So that's so far so good, and so far it probably looks exactly the same as their answer. I then thought carefully, because I've got z to the n minus 1, I thought, well, I'd better substitute z in. Now, remember, whenever you've got the c plus is format, the cos theta plus I sine theta format, you can always write it down in exponential form as well. An exponential form has an I in it, and then you've got to multiply by the argument. So it's e to the I pi over m. Now, you might also wonder, why is that to the power of n? Well, it's because in that summation, there are not n minus 1 terms. There are, in fact, n terms there because we started on 1. We started, if you like, on z to the power of 0. Can you see there? We go 1 up to n minus 1. So there's n minus 1 terms there, and there's 1 as well. So there's n terms there, and that's why that sum formula, which I've got here, that sum formula is for n terms, and there are n terms in that sum. Okay, so that's a couple of things I want to say. Now, straight away, I always prefer to try and work in exponentials if I can. So that z to the power of n is going to become e to the I pi over n, but I'm going to put that to the power of n minus 1 over e to the I pi over m minus 1. Apologies for my slightly scrappy handwriting, but I'm sure you can just about read it. Okay, that's the same as e to the I pi minus 1 over e to the I pi over n minus 1. Now, the top actually immediately simplifies because remember what I said, if you've ever just got e to the I pi, well, you can just think, well, how far am I turning from the positive x-axis? I'm turning all the way 180 degrees round, so that is going to be equal to minus 1. You can also determine that from the very famous, beautiful equation, e to the I plus 1, e to the I pi plus 1 equals 0. Clearly, e to the I pi is minus 1. So on the top, we have minus 1, which is minus 2. So far, so good, yeah? Now, on the bottom, we cannot simplify this one because it's e to the I pi divided by n, yeah? And I don't know, n's part of the generalization, yeah? It's like we don't know how many terms. There are n terms in this sequence. So I don't know what I'm doing pi divided by. I can't simplify that on the bottom. So if you like, so far, so bad, yeah? And so far, we haven't deviated from the textbook at all. Now, I want you to remember this step. Basically, if I can star it here, I'm going to show you the textbook's way of doing it, but I want to show you my way first, just because I want to show you what I was thinking. Yeah, you've got to be flexible in these questions in the way you approach it. Yeah, and sometimes you may find yourself wandering into the mathematical fog, but sometimes it will be okay. Yeah, and it's just about basically trying things and getting a feel for it. Yeah. So what I thought, okay, I've got e to the I pi over m. I could change that to cos of pi over m plus I sine of pi over m. But let's look at what I'm heading towards. I'm trying to get, I'm trying to get this result here. 1 plus I cot of pi over 2n. Pi over 2n. Now, cot is just cos of pi over 2n divided by sine of pi over 2n. But have you noticed we've got half the angle there? Yeah? That was what made me think, okay, I need half the angle here. So what I'm going to have to do is a bit of a fiddle. Yeah? I'm going to say, okay, e to the I pi over 2n squared, that would be e to the I pi over m. Yeah, and so I said, okay, and here's a big tip for you, let cos equal, let c equal cos of pi over 2m, and let s equal sine of pi over 2m. Yeah, great. Now what I can do is I can say, well, let's just scroll down. I need a bit more space. I can say that on my denominator, what I've really got here, I've got minus 2 over, now it was e to the I pi over m, but that's exactly the same as e to the I pi over 2n, which is c plus is squared minus 1. Oh, yeah. Now, the reason why that's c plus is because e to the I pi over 2m is cos of pi over 2m plus I sine of pi over 2m. Yeah? In other words, it's c plus is. Yeah? Now let's quickly work out what c plus is squared equals. You can just do it in a little, grid like this. And don't forget that I squared is minus 1. You're going to get c squared plus cis plus cis. And then you're going to get minus s squared because I squared is minus 1. So this is exactly the same as minus 2 over cos squared minus sine squared c squared minus s squared. This just saves you writing down loads of trig plus 2cis minus 1. Oh, but that's the same because we've got minus 1, c squared minus 1. Remember, that's cos squared minus 1, which is the same as minus sine squared, yeah? Because 1 minus cos squared is sine squared. I'm writing it without the arguments, which is a really bad habit. But therefore, cos squared minus 1 is minus sine squared, yeah? I'm going to rub that out before any other mathematicians see me write that. Always include your arguments. But yeah, I'm doing it just with c squareds and s squareds. It saves me so much ink. So that c squared minus 1 is minus s squared. So we've actually got minus 2s squared plus 2cis. Yeah? Now what I can do is I can cancel, can you see all the 2's in there? I can cancel the 2's. And I end up with minus 1 over, and I'm going to factorise out the bottom because there's an s in there. I'm going to say s times by, and then I need another ci, and I think a minus s. Yeah? Oh, great. Because what I can do now, really, there's only one thing I can do now. I've got an irrational denominator. And I don't like irrational denominators. Sorry, rational? What am I saying? I've got an unreal denominator. I've got a denominator with I in it, and I prefer I in the numerator, particularly when I'm trying to show it's 1 plus I cot pi over 2n. So all I'm going to do now is I'm going to multiply top and bottom by ci plus s. Oh, you're probably thinking you preferred the book's way of doing it. Well, it's okay. I'm going to talk about the book's way of doing it as well. But I'm just trying to teach you, basically flexibility in the way that you solve things. It's okay sometimes to do things differently. Yeah, that's going to give us minus ci minus s over, now what does ci minus s times ci plus s give us? It gives me I squared c squared, which is minus c squared. These two cancel because that's the whole point, and then minus s squared. So I get minus c squared, that's a c by the way, minus c squared minus s squared, yeah? So I get s times minus c squared minus s squared, but minus c squared minus s squared is minus 1 because it's minus cos squared minus sine squared, yeah? And so that's minus 1. I can apply it on the top and I get ci plus s. Oh, hang on, sorry, I've got to times the top. Oh, yeah, no, I've done that. Over s, and that is the same as 1 plus I cot of pi over 2n. And I hope you can see why. The s divided by s gives me the 1, and the ci divided by s, well, remember, c was cos of pi over 2n, and s was sine of pi over 2n. And so what we've got there is cos of pi over 2n divided by sine of pi over 2n, which is cot of pi over 2n, which is why it's 1 plus I cot pi over 2n. Okay, maybe you like that approach, maybe you don't. That's fine. I'm going to show you another way. I'm going to show you the book way now. So let's get rid of this. Just think, yeah, well, you've seen it on the video, yeah. I tell you what, I won't get rid of it. I'll just keep scrolling down. But basically, this is the way the book does it. It's we agree with exactly the same up to here, yeah? So I'm going to start from there. I'm going to prove it to you in a different way now. I'm going to show you the way the book approaches it. And it's a very, very sensible way. And you do need to understand this way because they use this in a lot of other questions as well. So we've got minus 2 over e to the I pi over n, take away 1. Now, their point is basically whenever you have this and you want to introduce a trig function, don't forget that basically e to the I theta minus e to the minus I theta equals 2I sine theta. Yeah, and that is literally this z to the z minus 1 over z equals 2I sine theta, which we were using in the last exercise. Do you remember that? Right, and that's when z equals cos theta plus I sine theta. So our theta here, well, what is our theta changed to here? Our theta changed to pi over n. So we can't introduce it straight away, but what we need is an e to the I theta minus e to the minus I theta. Well, I hope you can see that we can do that if we basically multiply top and bottom by e to the minus I pi over 2n. Yeah, and that is definitely the right kind of way to go, given that we're trying to derive cot of pi over 2n. Yeah, so I'm multiplying top and bottom by that. That gives me minus 2 e to the minus I pi over 2n over, and now we're going to subtract the powers there and leave ourselves with positive e to the I pi over 2n. I forgot the I. And then this is going to be e to the, oh, I've got that I down here. Can you see that? Careful with that. Minus I pi over 2n down there. Yeah? Okay, good. We're now in a strong position because if that's true, then and let's put those in coloured boxes so we can see it's not part of the argument because they're looking almost like part of the argument now. If these two are true, and they certainly are, well, then we can also say that e to the I pi over 2n minus e to the minus I pi over 2n, that's going to be the same as 2I sine pi over 2n. Yeah, and that's what I'm going to use next, or that's the way the book approaches it next. So we get 2e to the I minus I pi over 2m. But then down here, what have we got? We've got 2I sine of pi over 2m. Now, the lovely thing is, these cancel, yeah? Now, you've got an I on the bottom, but you've just got a single term on the bottom. So why not times top and bottom by I, yeah? That gives you minus I on the top, e to the I minus I pi over 2m, but it's going to give you I squared on the bottom, which is minus 1. And so just sine of pi over 2n. My working may be looking slightly different to the books, but it is exactly the same approach. I'm just talking through what they actually did. Now we've got the I on the top. I can make the two negatives make a positive, and I've got I times, now this is cos of pi over 2n plus I sine of pi over 2n. So I'm just using Euler's relation of e to the I theta is cos theta plus I sine theta there. And this is over sine of pi over 2n. And then basically I'm done. If I just multiply that I through, I'm going to get I squared. Oh, I've missed the minus as well. That minus is really important there, isn't it? Because that's cos of minus there, and that's going to be a minus in there. So I'm going to get an I squared. Well, let me just leave the I alone for a moment. I'll leave it in there. I'm going to get cos. Cos I can always make negatives positives. Sine I just have to make it a minus outside. And it probably does look slightly different to the way book's done it, but I don't think the book's that well explained, so I hope that this makes it a bit clearer what they're doing. And then finally we get to the answer, because I squared becomes minus 1, which makes that positive, and so we're going to get cot of pi over 2n just from doing the first term, the cos of pi over 2n divided by sine of pi over 2n, and then we're going to get plus 1, and we've got the I there as well, and we've done it. That's essentially the approach the book takes. It's both methods are valid. It's good to be flexible, and you definitely want to be aware of this result, which comes up really handy in plenty of questions. I think I'm going to cut this video short. It's going to take ages to upload, but I'm going to do example 14 for you next, because I do want to talk through that. We haven't got loads of examples of these kinds of questions, so that's why I'm trying not to do. I'm going to try and use these as examples. There are some more in the mixed exercise, and there's not many in this exercise, but I want you to have plenty to go on. Anyway, I've got another video ready for you. You can watch the next one as well. I hope it helps you understand this tricky topic. Bye bye.